Okay, welcome everyone to the 1W-MINDS seminar. This is the last talk actually in 2025, and it is my pleasure to introduce you Mariia. Uh, she is a collaborator with me in Munich. She's still in Munich. She's an excellent researcher. Unfortunately, she's not on the job market, but in the future, if she is, I think she's a valuable collaborator. And today she's going to talk about effects of depth in deep learning, independence versus recurrence.
So thanks a lot for the introduction, Edward. And also thanks for organizing, thanks for inviting me. I'm very happy to speak here, even though, of course, it's quite late where I am now. So indeed, I'm going to speak about the effects of depth in deep learning. And maybe let me first explain what I mean here by the effects of depth. So under the umbrella of the effects of depth of deep learning, there, of course, has already been quite a lot of work. And maybe most classically, most famously, this work is about expressivity of neural networks. So these are the results where people show how classes of functions that networks can represent get richer as the networks get deeper, right? This is not what I'm going to speak about here. What I'm going to speak is two very different aspects of depth and deep learning. So one research direction here is the signal propagation. Here we're concerned how to initialize networks so that the signals get stable as the networks get deep, and in particular, how to avoid vanishing or exploding gradients problem. And the second direction is the kernel regime of neural networks. This is more about training or generalization. And the question here is when or why deep networks behave as kernel models during training. And the common thing between these two directions is that both of these questions, they depend crucially on random initialization of neural networks. And therefore, these questions somehow demand probabilistic approaches, which I will focus on in this particular talk. And here I will talk about two different kinds of models, as you can also see from the title. The first one is the fully connected feedforward networks, where we have independent weights in all the layers. And the second class will be linear recurrent models, where we have the same matrix used in all the layers. So let me start with signal propagation in fully connected networks first. Here, the first thing that we should notice is that we can always see the signal flows in neural networks as these two coupled components that we usually call the forward chain and the backward chain, right? So in the backward chain, we compute pre-activations, which I denote here H, and activations X, layer by layer, starting from the input and going all the way to the output, XL, where L is the number of layers. And the equations that we use to compute this forward chain in each layer is, I think they're well known. So the pre-activations suggest the affine linear functions of the previous layer, and we get activations by applying the activation function phi to those, right? Now for the backward chain, here we compute gradients of a neural network using chain rule, also layer by layer, but starting from the output layer and moving towards the input. Here I denote this backpropagated variables, backpropagated gradients delta. This is what usually is computed in backpropagation algorithm and fully connected networks. The formula to compute delta L, given delta L plus 1, is quite well known. It's given here in the slide, right? So given this forward and backward chains, we can say that very broadly, the signal propagation literature asks basically how do the distributions of these variables H, X, and delta change as we move layer by layer within the chains, right? And so perhaps the most well-known result in this literature on signal propagation is the fact that in the infinite width limit of neural networks, we can actually compute exactly how the variance changes when we move one step in the forward chain or in the backward chain. So in this theorem here, just for simplicity, I consider a fully connected network of this constant width m, and I will always denote widths as m in this talk. And the weights here are initialized as Gaussians, with the variance also scaled by m, and with this hyperparameter sigma square. And what we have in the theorem, the main result, is that we have the exact expression of how the second moment of the forward chain changes when we do one step forward. And we have a similar expression for how the variance of the backward chain changes when we do one step backward, right? And maybe right now these expressions look a little bit unfriendly if you haven't ever seen them. But maybe the important thing to see here is that both expressions just depend on this expectation that is taken over this variable u, which is just a standard Gaussian, and everything else in these expressions is actually deterministic. In particular, this QL here is the deterministic variance, deterministic limit of the variance of the forward chain in each layer. And so these results are not mine. These results have been in the literature already for quite a while, and I give a couple of, I think, very famous references here. But I think that for the purposes of what we talk about further in the talk, it's nice to see how these results are proven. So I'll give you a short sketch of how you show this kind of results just for the forward chain. And also in the rest of the talk, I will only usually speak about the forward chain because it already gives a good idea of why things work, but the backward chain is similar, but usually a little bit more ugly. So this infinite width results of this kind usually depend on the observation that in the limit, the pre-activations in each layer become IID Gaussians. So the neurons become Gaussian and independent between each other in one layer. And showing something like this, in particular for fully connected networks, is quite easy. One can, for example, do this by induction and notice that layer L, condition on layer L-1 is Gaussian just because our initialization is Gaussian. But we have some, in principle, random variance of this Gaussian here. But by induction, we can show that this random variance, in fact, converges to a deterministic limit by the law of large numbers. And therefore, we can say that HL indeed converges to a Gaussian with a deterministic variance. So from this step, this is the most important step in these proofs. From here, the rest is just computations. So knowing that pre-activations are Gaussian, one can compute the activation expectation, just integrating over the Gaussian, and also compute one layer forward to express the variance of the next layer through the activation variance in the previous layer and the variance of this trace of the weights. But yeah, the most important thing is that infinite width limit relies on Gaussians here. So far, maybe this result looked a little bit not nice because the formulas were a little bit long. So the two corollaries of this result were it looks very simple, and these are maybe more well-known formulas. This is just the application of the theorem that I showed you before for linear networks and for real networks. Basically, in the linear case, the expressions that we had in the previous slide transform in a way that we just have both forward and backward chains multiplied by this sigma square hyperparameter as we do one step in the chain. And for real networks, instead, we have sigma w squared divided by 2. And these coefficients, they just come from integrating the Gaussian that I showed you before. So here in the picture, for example, I show that if you apply ReLU to a Gaussian and square it and integrate everything, then just ReLU eats half of the probability mass. That's why you get the 1/2 here. And so these results, they already give us the famous initialization scalings that are probably well known for everybody. So just for notation here, I define he, this variable he, is the expectation of the activation applied to the Gaussian that we have also here under the graph. And then we have the following situations for these linear and real networks. If he multiplied by sigma square is below 1, this is the situation where as the depth increases, both forward and backward signals, they vanish with depth, right? Then if this product is larger than 1, then signals grow with depth. And only when this product is around 1, the signals stay approximately stable. And the well-known initialization schemes, such as Glarot for linear networks or Hay initialization for real networks, they're based exactly on this, right? They initialize He square as sigma square as 1 divided by He. Okay, so this is all very classical results. But now we can ask a question. Okay, we derived somehow this initialization schemes in the infinite width limit. So it was some approximation. Do these schemes actually work for realistic deep networks? So where do the effects of depth come? And so to make this question a little bit more specific, to see what I mean here, we can speak about the following possible settings, I would say. The first one is what we just considered, the infinite width limit, where we have our m to infinity, then the depth here is fixed. So the depth to width ratio in the limit just tends to 0. We can also have another setting that is usually more challenging, the joint scaling limit, where we allow both depths and widths to grow, but the depth to width ratio is allowed to be some number that is not 0, right? And of course, there is the finite width setting where both M and L are just finite. And in some sense, of course, the finite width setting is the strongest setting because it just, in principle, contains both limits at special cases. Usually it's harder to derive finite width results. So after saying all this, what I want to show you is that for these linear and real fully connected networks, basically the same results that I showed you in the infinite width limit also hold infinite width. The setting here is exactly as before. We have this network of constant width, and the initialization is still the same Gaussian. And then these constants by which the forward and backward signals scale, they're basically the same here as we saw in the infinite width case. If you're very attentive, you can notice that for the backward chain, I here put the expectation outside of the ratio just to be precise, but maybe you can believe me that the difference here is quite small between the two things. And the proofs for this sort of results, they actually don't rely on any Gaussianity. So here you don't need the pre-activations to be Gaussian. In this simple setting in this simple setting of this theorem, we can just consider the ratio between the next layer activation, norm squared, and the previous one. And notice that by rotation and variance of Gaussians, we just have that the product of this matrix W and this vector XL cannot depend on the direction in X, but it only depends on the norm of X. So we can rewrite it as this norm of X multiplied by, again, some independent Gaussian U, which allows us, also using the homogeneity of the activation, to rewrite this ratio of interest as a sum of these terms that look like phi applied to a Gaussian. And everything here works in the finite case, so we can compute the expectation in the finite case. And then skipping a couple of steps here, we get the result that I show you in the theorem. For this sort of proofs, you can look, for example, on the paper that I cite here. But the point is, I think this result suggests that the answer to the question is yes, that the results of the infinite width theory for these fully connected, at least real and linear networks, give a pretty good idea of how also finite width networks work. But now let us move to a different setting, to linear recurrent networks. And so here we will look at linear recurrent networks as sequence models. So the forward chain will compute this activations H in each layer using the same matrix W at every either layer or time step. Here we will say time step. And also at every time we will add an input U, so we can see that the whole input is a sequence. And maybe you can say that these models are boring because they're linear, but in fact, these linear recurrent units, they have recently been used a lot as building blocks of state space models of things like Mamba. Of course, they're a little bit more complex, but people are quite interested in these linear recurrent units now because they appear to be actually useful in long-range reasoning tasks. But okay, so for this linear recurrent model, we want to ask the same question. How does the, say, variance of the forward chain behaves through the time steps? And I will again first give you the infinite width result here. So this is the infinite width result for the forward chain for this linear recurrent model. And I sort of on purpose give it to you here in a slightly counterintuitive way. Basically, what this theorem says is that in the infinite width limit, the variance of the forward chain of this model behaves as the variance of the model H tilde, where H tilde would be the same computational graph, but where the matrix W is sampled independently at each time step. So what this says here is that the difference between this model with tide weights, which makes it recurrent, and this model, but feedforward, where all the weight matrices are independent, is up to the order of O divided 1 divided by M. And this is in particular the result that holds in this famous tensor program framework that many people might know, which as a corollary gives us that the variance preserving initialization scheme for linear recurrent models is actually exactly the same as for linear feedforward models. So for linear feedforward models, we had Glorot initialization, where the appropriate variance scaling for the weights is 1 divided by M. And turns out that infinite widths, it's also exactly the correct scaling for recurrent models. So as I said already, I think that this result is quite counterintuitive, at least to me. So maybe I try to give you a sketch of a proof here. Unfortunately, I think there is no really short proof here. So what I give here is something that I think is a minimal proof that I was able to write here, but I think you still need to fasten your seatbelts a little bit for this slide because there is a lot of indexes. So suppose we consider the forward chains of these two models that we had in the theorem. One is where all the weights are tight, and one is where all the weights are independent in all the time steps, right? And now, since we're interested in the variance at time t, let us consider this just for being generic, the covariance term, where we take neurons I and j at time t and multiply them. And so what I did here, I just rewrote the matrix product that appears in the definition of H tilde through a sum over indexes over all these matrices. So it looks like there's a lot of stuff, but actually nothing happened. I just replaced the matrix product with the sum over indexes. But now what it gives us the expression of this Hi, Hj as a huge sum over some monomials, monomials in the Gaussian entries of these matrices that appear in the definition of H tilde. Okay, so since this is a monomial of Gaussian variables, we can actually use the Wick's theorem here to compute the expectation of each monomial. And so the Wick's theorem, I think it's sort of common in the literature on this, in the literature on infinite width limit of neural networks. And it essentially says that you can rewrite the expectation of the monomial of these Gaussians as the sum over all the pairings of indexes. And under the sum, you have products of covariances for each pair within the pairing. And so we can see that when we look at these covariances that appear in the Wick's theorem, they behave differently, of course, depending on whether the weights are tied or not tied. In particular, in the case where the weights are all independent, this covariance is non-zero only when all the indexes match. So both the indexes within the matrix and also the time index. But for the tied weight, what we have is that the matrix is the same over all the time steps, so we only need these lower indexes to match, right? So we see that in principle, in the untied case, there is fewer non-zero contributions. But actually, if you look at this sum of covariances, the total sum that appears here, the sum of monomials, well, it's not a very obvious step, but you can make yourself believe that actually even in the untied case, or sorry, even in the tied case, where all the weights are the same, the only terms that give you the contributions of order of 1 are actually pairings where there is no cross-time pairs within the whole pairing. So basically, you only need to count the pairings where the matrices with the same time index appear within these covariances. And I think maybe it needs a little bit like I'm not giving you really a proof here, but the mechanism to see this is that when you have each covariance that is non-zero, it gives you this contribution of 1 divided by m. And the sums over free indexes, this sum over ij, each free index gives you m. And so the only way to get a contribution of order of 1 is to exactly match the number of those. And if you look at it for a while, you can see that indeed this only happens without cross-time pairs. So in the end, what we have is that this cross-time pairings contributions for the case of feedforward networks with untied weights is just 0, like exactly 0. But for the tied weights, this contribution is at most of order of 1 divided by m for any fixed time t. And this gives us exactly the statement that we had before, that the infinite width limit signal propagation actually looks the same for these models. And maybe just to make it clear, so this is not exactly the proof that is used, for example, in the tensor programs. There it's a little bit more general. But for this Wick's contraction approach, I think that good reference could be this second works by Yaida. Okay, so now that we saw that indeed in infinite width limit, we have this counterintuitive results where the feedforward and recurrent case both have Glorot initialization as the stable option. We again have to ask a question whether it actually makes sense in reality for some sort of realistic networks. And I think an important consideration here is that linear recurrent units, they're explicitly models for long-range reasoning tasks. So large sequence length t is actually the natural operating regime. So maybe setting fixed t and going to infinite widths is not very natural here. And that's why in this part, we will mostly speak about this joint scaling of the sequence lengths and widths m. And so before I give you the actual result, let me maybe give you something that I think is a good intuition already. So consider this matrix W sampled from actually either real or complex Glorot initialization. So this is just the non-Hermitian Gaussian matrix. And let us consider how the eigenvalues of this matrix behave, in particular, the largest eigenvalue, which we also call here the spectral radius. So the picture is as here in the figure. Basically, in the infinite width limit, if we have a Gaussian matrix or Glorota initialized matrix, the eigenvalues converge to uniform distribution in the unit circle in the complex plane just by the famous circular law. So in the infinite width limit, the spectral radius is just 1. But in fact, if we want to account for the finite width correction to this spectral radius, the results in this theorem shows us that the convergence to 1 for the spectral radius is in fact from above, and the size of the correction at finite widths is roughly of order of 1 divided by square root of m. Okay, so the spectral radius is a little bit larger than 1, actually. And I don't know about you, but so to me, it already seems that this gives us a good reason to believe that if our sequence length is at least of order of square root of m, then we will have some sort of instability when we take powers of this matrix, right? And in fact, it will be maybe important later that this theorem on top of the size of the correction also tells us that the spectral radius behaves as a Gumbel variable here. We also have the shape of distribution. Okay, but so for me, this kind of intuition so far already suggests that this time for recurrent networks, the answer to our question is no, that in fact we will not have infinite width initialization behave behave stable in the large sequence length setting. So this is the actual result that we have in our recent paper that computes the lower bound for the variance of the forward chain of this linear recurrent unit. Here we consider complex Glorota initialization and isotropic Gaussian input. And we see that the variance of the forward chain grows at least exponentially in this term of t squared divided by m. And the limit here is taken in under the joint scaling, where we let both m and t to infinity, but t squared divided by m is tends to some constant alpha, right? So that's the particular joint scaling. So what we have at large sequence lengths, basically this exponent dominates the behavior of the forward chain. On the other hand, if you remember our infinite width analysis, so at infinite widths, at most what we could get for such a forward chain would be like O of t, right? So this infinite width analysis here doesn't see this exponential growth for large sequence lengths. Therefore, we see that the finite width corrections in this case actually reveal the instability that was completely hidden by this infinite width analysis, where we have hidden everything under O of 1 divided by m. And the analysis that we do also shows us the actual difference between recurrent and feedforward networks that also wasn't really visible in the infinite width analysis. So our result, this result that I showed here, it depends mainly on this lemma, which I call the variance lower bound. This lemma essentially gives us a lower bound for the expectation of this case moment of matrix W, which is Glorota initialized, multiplied by some Gaussian vector U. And you can see that this lower bound, we derive it for the finite k and m. So it's a finite width result that we will later use to derive the double scaling results. So the proof here is quite simple. First, we express the expectation as a trace. And the second step, it just says that the lower bound for the trace is given by the sum of the eigenvalue moments. because the trace of interest here is the sum of singular values, singular value moments, which is here indeed lower bounded by the sum of eigenvalue squared moments. And I mean, I showed it by Schur decomposition, but I think it's also a well-known result. And the remaining part is just to show the expectation of the eigenvalue moments, which we can do in this case using the known expression for the one-point density of the eigenvalues of Gaussian matrices, which is also a known expression. It's due to Ginebra. The expression is like this. Maybe don't look at it too much. It's quite ugly, but you can believe me that if you integrate it with correct scalings everywhere, then we get exactly the expression that is shown in the lemma. Okay, so now that we have this lower bound, when we nicely scale it by the square root of our width, what we get is that in our limit of interest, where we scale here k together with the square root of width m, we get exactly the exponential limit that we saw before, where we have the exponent of alpha square and divided by alpha. And this is exactly the expression that ultimately leads to our lower bound for the forward chain. I already showed this result before, so I'm just showing it again so that you compare that the expressions are pretty similar here. Okay, so again, maybe why it is important, why it seems important to me. I think that this result just gives a concrete example where this infinite width analysis actually gives a qualitatively incorrect description of the signal propagation behavior, even in the simple case of linear network with tide weights. In this paper, as a bonus, we also derived a rescaling of growth initialization that actually allows to avoid this explosion. So this part is a little bit theoretical, less theoretical, but what we can say here is that if you remember that the spectral radius, let's say, is approximately Gumbel, then we can use the quantiles of the Gumbel distribution to derive this approximate upper bound for the spectral radius. And this allows us to use this upper bound to rescale our growth initialization, which allows us to roughly shift the spectral radius below 1 with probability p, which we can control. And in practice, if we use something like standard deviation here for the quantile, then we can already see that such initialization likely avoids the exploding behavior of vanilla growth here. Okay, so this was all about the signal propagation behavior in general. Now we saw that the depth or the joint scaling of depth and width at least indeed changes the behavior of the recurrent networks quite a lot, but we didn't really see whether this finite width effect or joint scaling leads to some, let's say, surprising behavior in feedforward networks case. So far we saw that the variances of both forward and backward chains in feedforward networks actually don't show any, let's say, surprising depth effects. But in fact, the finite width effects do become significant also for feedforward networks, but not just on the variances of forward-backward chains levels, but for the kernel regime this time. So since I'm going to speak about the kernel regime, let me just quickly define it in case people have not seen it. So the kernel regime, in the kernel regime literature, the key object is this neural tangent kernel, which I denote theta. And it is a kernel defined as defined for a neural network with output function f as inner product of the gradients of f with respect to trainable parameters w computed on these inputs xi, xj. And so this kernel it is important because it controls the first order approximation of the gradient descent dynamics in neural networks. So if we want to see how the output function f changes when we do some gradient descent step, we can write it as a product of our kernel theta and the gradient of the loss function with respect to this f, which is basically just the residual. But of course, this form of the dynamics still doesn't give us that much because it is still intractable, since this kernel changes over time, and it also is random because it inherits randomness from initialization. So even though the dynamics looks linear, in fact, it's very much not linear because theta is not a constant. But the kernel regime is actually one case where this dynamics does become tractable, and it happens most famously in the infinite width limit of neural networks that we already talked about a lot, where there are two important results. The first one is that the NTK actually becomes deterministic under random initialization. So we have that theta times 0 converges in probability to its expectation, which I denote here as deterministic theta star. And also the kernel remains constant during training. So theta at every time t converges to its value at 0, which is equal to theta star as well. So these two results basically allow us to look at the dynamics, this first order approximation of the dynamics as a linear ODE. And it makes it exactly equivalent to the dynamics of kernel regression with the constant kernel theta star. And since for kernel regression, we can write explicit solutions for the gradient descent dynamics, and we can also derive generalization results, we can do all the same in the kernel regime. So we have analytical solutions, and we can derive all the properties of trained networks that we want here, including generalization bounds. And this is why the NTK regime is very popular in papers to show theory on neural networks, right? But again, this infinite width limit was, this kernel regime results, they're derived in the infinite width limit. So we can again ask the same question we did before. Does it work for realistic deep networks? Do they still converge to kernel regime? And again, since we speak about depth here, we will speak about deep networks from the point of view of the joint scaling limit. And the picture here is a little bit complicated. It's effect like this. So if we consider fully connected feedforward networks with biases, and biases are important here, then the picture that gives the answer to this question looks like this. It's like a phase diagram where on the x-axis we have the initialization scale, so our parameter chi square. And on the y-axis we have the depth to width ratio, which we usually denote lambda. And so in the green area, which happens for relatively shallow networks or for networks initialized in this zone where chi by sigma square is smaller than 1. Here we still can show the same convergence to the NTK regime that we have in the infinite width limit. But actually in this orange zone, when networks get deeper, the convergence to the NTK regime doesn't happen anymore. And so this picture, this diagram is just made by hand. So it's like an approximation. But this is how it's in fact looks in practice. These are some experiments. So what these two pictures show is the NTK dispersion. Dispersion here is the ratio of the second moment divided by the squared first moment. And so here in the black area, you have the dispersion being close to 1, which means that the variance is close to 0. So the kernel can be approximated pretty well by its expectation, right? But when we get to this red zone, the dispersion approaches 2, which means that the variance is large in comparison with the expectation. So the expectation doesn't really give a very good approximation of our kernel value, which is of course makes it strongly not deterministic. So okay, one may ask if we didn't really see the what we call this different effects of depth, if we didn't see any problems with the infinite width limit approximation in the previous part of the talk, why do they happen here? Why do we have a different behavior in practice and in the infinite width limit? And I think a nice answer here is that the relevant quantities for the kernel regime, they don't depend just on the variances of the chain that we had in the previous part of the talk, but they depend in fact on higher moments. Specifically, the dispersion depends on the force moments of the forward and backward chains. And these force moments are in fact, even in the feedforward case, affected by the finite width effects. And therefore, you can see this noticeable depth effects or finite width effects in this case. So the diagram that I showed, the phase diagram that I showed you before, it was kind of a qualitative picture, but we also have the quantitative law here. So this is the result, again, for simplicity, for constant width networks, but it's a result for the NTK dispersion in the joint scale in infinite depth and width limit. And what we have here is three different expressions which correspond to these three different settings of sigma w square, which are either sigma w square larger than 2, where, as you may remember, signals grow with depth. Then we have the result at the middle when sigma w square is equal to 2, so this is the stable initialization. And we have the case where sigma w square is smaller than 2, which is the vanishing case. So in the first two cases, we have exponential growth of the dispersion with the depth to width ratio lambda. And in the last case, we have the convergence to 1, which is exactly the same we would get in the infinite width limit for any value of sigma w of sigma square. So you see that basically this result in comparison with the infinite width limit, the infinite depth and width limit actually lets us see the divergence of behaviors depending on the setting. And on the right, actually, you can see the experiments that are just here to confirm that the expressions here are exactly right. So you see the theoretical lines, these straight lines, and also the results of sampling the NTKs of actual networks. So you can see that indeed the lines follow the theoretical expressions pretty closely here. Okay, so maybe let me again explain a little bit why this happens. So why, where the deviation from the infinite width limit comes from here. And the important thing in the forward propagation case is that, so you remember before we only looked at the ratio of expectations between this second moment of activation layer L plus 1 and layer L. And you remember that we got something like this, that the ratio of the second moments is equal to sigma square divided by 2. But for the purposes of the kernel regime and the force moments of the chains, now it is also important to look at how the second moment of this ratio looks. So we need to look also at the expectation of this variable nxl squared. And what we will see if you compute it, it's also computed in the paper they cite here, you would have the expectation of the square being just square of the expectation multiplied by 1 plus this small term equal to 5 divided by m, which is of course something that vanishes with depth, but, vanishes with width m, but can accumulate through large depth again. So to see this effect in the most maybe simple setting, like we're not going to compute the NTK here, but we're going to just look at the force moment of the forward chain. What we can do is write this force moment as a telescopic product of these variables nxl. And essentially what happens is that when we multiply many expectations of nxl squared, we multiplied many terms of this form of 1 plus 5 divided by m. And when we take this guy to the power L, eventually we get the exponents again, right? So a little bit similarly to how we saw this joint scaling limit for the forward chain in the recurrent case gave us exponents under the correct scaling. Here we also have this exponential accumulation of small effects over large depths, which also brings us this exponential scaling. So basically we see that here the depth again leads to this accumulation, but again, only in the fourth moment, but not in the second moment. Okay, so in conclusion, what we saw is that for fully connected feedforward networks, the depth or the finite-width effects, again, doesn't really affect the second moment of the computation chains, which gives us that infinite-width initialization schemes, such as the famous Gorod or Hare schemes, they remain relatively stable for large depths, at least on this variances level. But the depth here changes the force moments of the computation chains, and therefore it disrupts or potentially disrupts the convergence to the kernel regime. On the other hand, if we look at linear recurrent networks, here the depth already changes the second moment of the forward chain in comparison with the infinite width computations, and therefore infinite width initializations such as Glarot quickly become unstable with depth. But overall, this recurrent setting is much less studied, and many questions here still remain open. Okay, so then that was it, and thank you for your attention.
Okay, thank you, Mariia, for the very nice talk and the different scaling. We're open for question, and if not, I will be the first to ask, I suppose. When you talk about this